Hello, we're Team 1155 for the SCUDEM 2025 competition. We're doing problem C, birds of different feathers. My name is Nguyen.
I'm Joseph Raogninirina.
My name is Jose Castro.
And we're from the University of Houston.
Research shows that animals from different species often form mixed groups for survival advantages like improved foraging and predator detection. In the paper, Mixed Species Herding Levels the Landscape of Fear, the author provided some empirical data on how herd composition and social interaction affects predator detection. They used behavioral and ecological variables to study and report on the effect of heterogeneity of the herd on the improvement of predator detection. Building on those ideas, our goal for this project is to mathematically model these behaviors and to simulate how the composition of a herd and the dominant skills of each species influence predator detection, and to measure how interspecies communication improves group awareness. To make the model manageable, we assume that our environment takes place in the African savanna under constant temperature and sunny weather so that external factors like rain and winds don't affect sensory skills. Initially, no animal is aware of the predator. We also define specific traits for each animal in our model, like buffalo has moderate awareness, ostrich have good eyesight due to its big eyes, zebra have good hearing, impala have good vision, and giraffe have good vision range due to its height. We made this distinction to give us a realistic differences in detection skills that we can translate into parameters in our equation. For parameters, capital N has the total number of species in the herd, and for every species, Nj is the total number of individuals of that species, and Aj of T is the number that are aware of the predator at the time T. Alpha J is the detection rate or vigilance, which measures how effective each species senses danger, and it varies over time. Next, we have the communication rate, CJJ, which measures how well awareness spreads within the species. For example, a buffalo warning other buffalo, and CKJ, which measures cross-species communication. For example, a zebra responding to an ostrich alarm call. These terms leads us to a system of coupled equations describing how awareness changes over time through both detection and communication.
We define our detection rate of species J by alpha J as a combination of their sensory skills, like speed, vision, smell, hearing, and how much they rely on each skill. From the equation beta J, which is the skill, and omega J, which is the weight of each skill. For the weight of each skill is important because in the real world, different animals may have a higher priority for skill. For an example, the ostrich can see really well, so its vision is weighted higher compared to the sense of smell when it comes to predator detecting. We also have the communication rate for interspecies and cross-species. With the communication rate, we thought about two parts, signaling and receiving. Within a species, the rate depends on how they signal and receive. Like when an ostrich senses danger, they will make a noise. Another ostrich can pick up on that noise and know that there is danger nearby. For a cross-species, the communication involves signaling from species K and receiving from species J. This is our ODE model of the rate of change of awareness within the species over time. The first term shows the direct detection of harm, where alpha J is the detection rate that we discussed earlier, and Nj minus Aj is the unaware population. The second and third term represents information spread for within and between species, dividing by Nj normalizes for group size. This is a matrix that we gathered from our dataset cited below that allows us to see the communication rates between species. We can see that the highest values are along the diagonal, which is when animals communicate with its own kind. Ostrich can be seen having the strongest rates of all, whether if it's with its own species or other species. Buffalo mainly communicate within their kind. This can be seen when the inter-communication rate is higher for when it's by its own species and lower for when it's cross-species. And zebras can be seen having the weakest overall communications, whether if it's with its own species or different species. So we're using the Gisby stochastic system algorithm to simulate our model. The reason why we're doing that is because in real life, animals doesn't follow a smooth curve. Using this algorithm allows us to account for randomness and unpredictability, just like real life animal communications allow the realistic variability. This is more biologically realistic comparing to a smooth ODE curves that MATLAB can generate you. This is the algorithm that we have created. This is the important structure of the algorithm. The first half is a structure of the ODE, where we have the equations that we formulated earlier. The second half followed the Gisby SSA structure, for which to generate random events of time for detection and communications. This goes on for a loop until all the animals became aware, and then it exits the loop. We were able to simulate 3 different models, one for when there's only 1 species in an environment, one for there's 3, and one for there's 5 species. Doing this allows us to see the interaction between species as they cohabitate and detect a predator. Here we have when there's only 1 species in an environment. The buffalo curve seems to have a linear trend here. And here we have a model of 3 species, the buffalo, ostrich, and zebra. We can see how awareness grows faster here. Ostrich communication influences the buffalo's curve upward. This shows how communication of a strong communicators group accelerates the awareness. When there are 5 species in the environment, we can see that the buffalo's curve showing a narrower logarithmic growth, but their improvement is minimal. We can also see that the zebra's curve is also showing an upward trend. This is because the impalas is also accountable for, and the impalas, as we see in the matrix, it is the second highest communicators. So talking about the detection speed, we are made aware that 50% awareness was met at 240 minutes for when there's only 1 species, 175 minutes for when there's 2 other species with the buffalo, and 150 minutes for when there's 4 other species with the buffalo. This is 27% increase in awareness going from 1 species to 3 species, and 38% awareness increase going from 1 species to 5 species. Why is this important for us? This is important for us looking at this in a biological sense, not just mathematics. This let us see that 3 species in an environment helps tremendously in terms of awareness, but as it approaches saturation, which is 5 species, those extra species still help, but not as much.
From the graphs, we make the following observations about each model. The first model shows a somewhat linear relationship, meaning the animals, in this case the buffalo, becomes alerted at a constant rate. When looking at the second model with 3 species and focus on the function for the buffalo, we start to notice a difference towards the middle of the function. More buffalo become alerted within the same time when compared with the first model. The same trend happens in the third model, but now we begin to see a concave shape for the function of the buffalo. In conclusion, from the second and third model, we see that as more species are added, the buffalo population becomes aware of predators faster, so adding more species does make a difference. The difference in awareness for the buffalo is apparent from the second model onward, and we start to notice a concave shape for the function of the buffalo in the third model. With this, we can conclude that at least 3 different species are needed for there to be a non-trivial advantage in multiple species groups. And because for the third model, the function for buffalo becomes concave, we conclude that after a group of 5 species, less difference will be noticed. The limitations for this model were that we assume the specific environment and species, when in real life we have multiple environments in which species group together, like in the sea or air. We assume fixed population for each species, when in reality this number varies by setting. And lastly, we gave only 1 skill to each species, and species can have multiple good senses, and how good each sense is depends on each animal. These are our references, and thank you.